Okay, in this video I'm going to talk about a system that starts at equilibrium, and I'm going to change the temperature of that system and look at how the equilibrium shifts. To do this, we're going to have to put a whole bunch of stuff together. We're going to have to talk about our Maxwell-Boltzmann distributions, and we're going to have to talk about activation energy and a bunch of stuff from this unit and the rates unit. So let's look at this reaction. We're going to consider nitrogen dioxide going to form dinitrogen tetroxide, and we're going to see that this is an exothermic reaction. This is an energy producing reaction. What that means then, if we remember our diagrams for chemical potential energy, is that since it's an exothermic reaction, it's going to start up here, it's going to go through some activation complex, and then it's going to come down to a new level of energy. What we can see from this diagram, the important aspect of this, is that the activation energy of the forward reaction, that I'll call EA1, is smaller than the activation energy of the backwards reaction. If I were to try and go this way, my activation energy would be here. And if I were going to try to go this way, my activation energy would be here. So EA1 is less than EA2. This is because it is an exothermic reaction, meaning that energy is being produced, or we've gone to a lower state of energy. So from the higher state of energy, the activation energy isn't that high, the activated complex isn't that high. From the opposite direction, the activation energy coming from this lower state of energy is quite high. It has to get up very high. Now, we're also going to consider our Maxwell-Boltzmann distribution. Let's say that our original temperature left us with a Boltzmann distribution that looks like this. And let's just pretend, for the sake of argument, that the activation energy of the the reverse reaction was way up here, EA2, where the activation energy of the forward reaction is somewhere down here, EA1. And so, at our regular temperature, the forward reaction is happening, or the reverse reaction is happening this much, and the forward reaction is happening this much. That would make the forward reaction naturally faster. That would get compensated for by the populations of the two species. There'd end up being more forward reactions favored, so more products than there are reactants, and then the two reactions rates would balance out at that concentration level. Now let's imagine that we make this system colder. So to make it colder, I'm going to go to blue, because that's what I think cold should be. And what that means then is that my Maxwell-Boltzmann is going to shift to the left like this. So this is colder. What we can see here is that while the activation energy, or the number of particles going in the for the forward reaction, has been reduced, the number of particles that are above the activation of the energy of the reverse reaction has almost been completely wiped out. What this means is that both forward and reverse reactions are slowed. But look at this tiny little bit of a population that can still go backwards. What that means then is the backwards is slowed more than the forwards. Because the activation energy associated with the backwards reaction is larger, the reduction in temperature causes a greater effect on that overall reaction rate. What that means then is, if we consider the original reaction rates to be equaled out at some value, they're both getting smaller, but this guy maybe is only shrinking in half, where this guy is almost completely disappearing. What that means then is that the equilibrium is going to shift to the right. Eventually, the population of N2O4 will build up such that these two reaction rates become equal again. But in the meantime, more N2O4 is going to be produced. Not only that, but more energy is going to be produced. So while we made it colder, as Le Chatelier would have predicted, the equilibrium has shifted to try to produce more energy to contradict that change. And so it's heated it back up a little bit. So here, if we had our concentrations of NO2 and NO4, and we're floating along at equilibrium, when we cooled it, because the energy is on this side, to try and heat it back up, the reaction went this way more than it went this way, or because the reaction rate of the reverse reaction was slowed more than the reaction rate of the forward reaction, what that means then is we ended up with more products and less reactants, and more energy to try and bring the system back up to temperature. Let's try and have that same discussion, but from the perspective of heating the environment. And this time we'll start by talking about what Le Chatelier predicts, and then we'll go and talk about how that makes sense with regard to the relative reaction rates. So here's our Maxwell-Boltzmann, and here's what we would define as where we start, and here's our equilibrium. NO2, two of them, going to form N2O4 and energy. So let's imagine that we heat this system up. Le Chatelier tells us when the temperature is raised, the system will respond by trying to undo or resist the change. So if the temperature is raised, that means there's extra energy, so the reverse reaction will be favored in an attempt to use up that excess energy. What does that mean for a Maxwell-Boltzmann? Well, heating it up means making the energy profile go out further. Now if we go ahead and put our two activation energies back on this graph, we can see that while there are more particles available to do the forward reaction, that change isn't that significant. Alternatively, if we look at the number of particles that are now available for the backwards reaction, it's much, much higher. So while both reaction rates speed up, the forward goes a little faster, maybe even twice as fast, but the reverse goes way faster, having so many more particles that are now available for that reaction. And so now the backwards reactions change is much greater than the forwards, and as a result, the overall shift here is to have the NO2 particles building up, slowing up this reaction, and speeding up this reaction until the two are equal again. So the backwards reaction is favored, just like Le Chatelier said, because the change in the number of available particles caused by the temperature was greater for the backwards reaction with the greater activation energy than it was for the forwards reaction with the lower activation energy. Just put some words to that. So both forward and reverse reaction get faster. However, the reaction with the greater activation energy is more affected by the change. Affected by the change. This means the backward reaction becomes faster than the forward reaction. Shifting the equilibrium. Again, if we trace a plot of our relative populations, we said we were going to start at equilibrium, so the two things have become stable. Then, when heat was added, to use up the heat, the backwards reaction was favored, so some of this got used up. And as a result, some of this got created until some of that energy got used up, but also until those reaction rates became the same again. So Le Chatelier tells us the simple answer of what's going to happen with the reaction rate, but that's why changing temperature has more of an effect, or that's why changing temperature shifts in equilibrium. Remember, changing temperature affects the reaction with the higher activation energy more than the reaction with the lower activation energy. And so by figuring out if it's endothermic or exothermic, we can figure out which reaction will be affected more and predict what will happen when we change the energy of the overall system or change the temperature.